Let's begin by formalising this notion of a linear model with a bit of notation. So, assume we have a training set of n samples, and each sample consists of a pair x, which is a d-dimensional vector of d real numbers, and y, which is a single scalar real number. For the time being, we're going to limit ourselves to the scalar output case. The model generalizes quite naturally to a vector output, but in practice this is equivalent to fitting separate linear models for each of the output elements, so without loss of generality we can focus only on the scalar case for the time being. Given this training set, what we would like to find is a vector w, which is also a d-dimensional vector, such that when you take the dot product of that vector with the input values for any training sample x, then the result of the dot product, which we will call y hat, where the hat just represents that it's an estimate, where that dot product output is in some way, on average, a good model of the true y values. A convenient bit of notation here is to pack all of the training set inputs into a single matrix, which we'll call capital X, and in this matrix, which is known as the design matrix or the model matrix, all of the features, that is to say the individual dimensions of the input vectors x, are columns in the matrix, and all of the individual samples, that is to say each sample x, is a row in that matrix. Correspondingly, we will pack all of the ground truth values y into a single column matrix, such that each of the rows in that matrix is the ground truth corresponding to the matching row in the design matrix. Given this construct, the whole model can be compactly written in this notation as y hat equals capital XW, where the y hat is now also an n-dimensional vector of all of the estimated y values. This design matrix notation will be used a lot in the weeks ahead. One thing to note about the model as we've expressed it so far is that it does not contain any constant offset or intercept or bias term. There are a number of ways in which we can introduce this into the model. We could add it explicitly as a separate term, such that the overall model would then be rewritten as y hat equals x times w plus b, where b is the new bias. Alternatively, we can consider the intercept to be an additional element in the weights vector to be estimated. So we add an extra weight dimension w0, and all of the input feature vectors, the x's, will be augmented with a dummy feature which always has the value 1 to correspond to this intercept term. A third approach is to hive off the estimation of the constant offset or bias into a separate process and assume that it is not present for the purposes of our estimation. One way to do this is to standardize all of our input features. They will then have an expected value of 0 and will contribute nothing to the output. And at this point, we can set our offset or bias just as the mean value of the ground truth values y. This linear model, as we have described it, has a convenient and intuitive geometric interpretation. If we consider each training sample, the pair x, y, as a single d plus 1 dimensional vector that has all of the x elements and the y in a single vector, each of those will be defining points in a d plus 1 dimensional space, and the model y hat equals x times w will be defining a hyperplane, a d-dimensional hyperplane in that d plus 1 dimensional space. This kind of hyperplane is very easy to visualize for one-dimensional input features. It's just the familiar trend line on an x by y graph. Visualization is a little bit murkier with two input dimensions, because then we have to deal with a 3D d+1 dimensional space in which we're plotting a plane through a bunch of points, but it's still pretty intuitive. At higher numbers of dimensions, it becomes more or less impossible to visualize, but the principle is still the same. In this interpretation, the vector w determines which hyperplane is produced. But which hyperplane do we want? In other words, how do we choose w? Any w would represent a hyperplane, so how do we choose which one? What are our criteria for choosing? Obviously, we would like the best hyperplane that best models the data in some way. Therefore, we need some metric of goodness or badness, in other words, a loss function. We're thinking about this geometrically, and so it seems plausible that distance might be a useful metric. In fact, we're going to use the distance between the true value of each point and the predicted value. In other words, it's y minus y hat. This is often known as the residual. The true value may be above or below the hyperplane of predictions, and so this residual is signed. It may be positive or negative. We don't want to be able to offset really terrible errors in one direction with really terrible errors in the other. That doesn't really mesh with our ideas of what might be a good fit. And so we want to get rid of that signedness, and to do so we will take some kind of norm. Other values are possible, but in practice it is mathematically convenient to use the Euclidean or L2 norm, or in fact its square. This choice may seem slightly arbitrary, and we will come back to some of the reasons for it later, but remember that one of our goals in choosing a loss function is that it should be optimizable. So for the moment, let's just note that this will be. Each of the points in the training set has its own residual, so we're going to need to aggregate across all of them. In other words, we'll just take their sum. We can express this like this, or equivalently like this, or equivalently like this. This, in fact, is our first loss function, sometimes known as the residual sum of squares. All we have to do now is minimize this, and the problem is solved. So what we're looking for is a vector w star. You'll recall the star notation from last week's lectures. Vector w star, which is the value that minimizes this loss. As luck would have it, this problem is convex and differentiable, and as previously mentioned, it has a closed form solution, which we'll derive in a minute. First of all, a little sidebar on notation. We're going to need to take the derivative of the loss with respect to the vector w. So w is a vector. What does it mean to take the derivative with respect to it? The way that we're going to deal with this is to take the partial derivatives with respect to each of the elements of w and construct a new vector, which is the vector of those partial derivatives. It will be the same size and shape as w itself. We denote this vector of partials with this symbol, which is known as nabla or del, but we will usually just call it the gradient. This is really a special case of the Jacobian matrix, which is a representation of the partial derivatives of a vector function with respect to vector inputs. Before we get into the derivation of the closed form solution for the least squares problem, a couple of identities that we're going to make use of, that it's useful to recall at this point. Matrix multiplication is not, in general, commutative. but there is a version of it that is commutative if you also transpose. So A times B, take the transpose of all of that, that's the same as B transpose times A transpose. The single dimensional case of this is A transpose B equals B transpose A. This in effect is just reminding us that ordinary vector dot products are commutative. I'd also like to just introduce a couple of standard gradients for particular kinds of term in matrix expressions. The first is a basic linear form, so the gradient of the inner product of one vector by another with respect to one of those vectors is just the other vector. And this is the gradient for a quadratic form. In this case, you have some vector x, where you take x transpose multiplied by itself with some symmetric matrix in between. In this case, the gradient is just twice that symmetric matrix times x. These two gradients are really just generalizations of the familiar linear and quadratic terms in ordinary scalar differentiation. We're going to start with some rearrangement of the loss function as we've currently defined it. We'll start by expanding out the multiplication that's implicit in the squared term. So we basically just take one copy of xw minus y and multiply it by another. We do this term by term, just as you would in any kind of binomial product. This gives us the four terms that we see here. For the first term, we have this xw transpose. We apply our identity of multiplying and transposing, and we turn that into w transpose x transpose. The rest of that term remains the same. For the second term, we'll use the vector form of that identity. X times w is just a vector, y is just a vector, so xw transpose times y is the same as y transpose times xw. The third term is already the same as this, so we can just add these together. And the final term we're going to leave as it is. Matrix multiplication is associative, so we can do a bit of re-bracketing here, which we do both in the first and second terms. We're again going to leave the first term as it is. We're going to once again apply the transpose identity in the second term, so it becomes 2x transpose y all transposed times w, and again the last term remains unchanged. This then is our rearranged expression. At first sight, it doesn't seem particularly more tractable, or certainly any simpler than the original form, but now we come to take the derivative. So the gradient of the loss with respect to w is the gradient of this whole expression. Let's look at this first term. X transpose x is by definition symmetric, so this first term is a quadratic form, and we know what the gradient for that should be. In the second term, x transpose y transpose is just a vector, so this is just a linear form, and again we know what this should be. Finally, y transpose y doesn't involve w at all, and so we can just get rid of it. We want to find the minimum, so we can just set the gradient of the loss with respect to w to 0, and that will tell us the value for our w star. We can just rearrange this expression, cancel the 2's, and there you have it. This is the answer. The optimal w is x transpose x, take the inverse of all of that, times x transpose y. One thing you may have noticed in that derivation is that we've assumed that x transpose x is invertible. There are two important cases where this fails. The first is that you just don't have enough data. In that case, the problem is underdetermined, and you have too many unknowns for the amount of data that you have. There are really two possible approaches to this. The first and ideal is to get more data. If you really can't do that, then you need to reduce the number of features that you have. We'll discuss some methods for feature reduction later in these lectures. Another situation where a non-invertible x transpose x might arise is if your features are not linearly independent. In this case, what you will probably want to do is get rid of some of the redundant features. Again, you can do this explicitly, or there might be some other feature selection techniques that you could use that we will discuss later. You could also attempt to address this problem by applying regularization. Some regularization methods have the effect of making your features less correlated.